Howdy, this is Jim Rutt, and this is The Jim Rutt Show. Listeners have asked us to provide pointers to some of the resources we talk about on the show. We now have links to books and articles referenced in recent podcasts that are available on our website. We also offer full transcripts. Go to jimruttshow.com. That's jimruttshow.com. Today's guest is Dan Schrag. Dan is the Sturgis Hooper Professor of Geology at Harvard University, Professor of Environmental Science and Engineering, and Director of the Harvard University Center for the Environment, as well as external faculty at the Santa Fe Institute.
Hi, Jim. Great to be here.
Hey, great to have you here, Dan. This is the third episode in our series on climate science and responding to climate change. Let's start with, how did a geologist get interested in climate change?
Well, as a geologist, I'm actually a geochemist. My interest really came through trying to reconstruct ancient environments. A big part of my work involves studying Earth history. I'm interested in how the environment has changed over time, over billions of years, over millions of years, over thousands of years. And that includes the record of climate change in Earth history. And in some ways, our understanding of the future of climate change rests heavily on our understanding of natural climate variability in the past. The Earth has experienced huge climate changes over various timescales, but this is nothing like what we've experienced in the past. But it still frames our understanding and helps us constrain the range of possible outcomes.
Yeah, and as I understand it, the range is really huge. I mean, back to the snowball Earth, is that still a live hypothesis that at one point the Earth was almost entirely covered with ice?
Absolutely. And there are even lessons from the snowball Earth for our future as well. There have been extreme climate changes over Earth history. And I think for me, they've helped me appreciate what I think of as the timescales of climate change. And that's, I think, an interesting part of it. Starting about 20 years ago, I was mostly working on paleoclimate, but I would give talks on climate change, and I would give a talk about the history of climate. You probably saw me give a talk like that at Santa Fe many years ago, and would end, and maybe in the last minute or two of the talk would arm wave about what we should do about it. And I think I began personally to be very frustrated with that I wasn't happy giving a talk about a huge problem that was a planetary crisis, but didn't have much to say about what we should do about it. And so I actually started systematically thinking and studying and working on devoting a part of my research effort to thinking about energy technology and then eventually energy policy as well. And so that's become a big part of my portfolio as well.
Cool. Yeah, I've heard you talk on the topic multiple times at SFI. I actually attended the first SFI Climate Summer School where you talked at, as I recall.
Oh, wow. That's a long time ago, I think.
Yeah, it really was. I remember the crowd trying to hush me when I started asking questions about geoengineering, as if that was a bad thing to talk about. But we'll talk about geoengineering.
Oh, I hope we'll talk about it. It's a very important thing to talk about.
Exactly. I was into geoengineering when geoengineering wasn't cool. So one of the things about the history that has caught my attention is I've read a paper, not too long ago, about sometime in the not really deep ancient past. I believe it was when we were coming out of one of the ice ages or one of the fluctuations around ice age. There was a very rapid increase in atmospheric temperature, approximately 15 C degrees in 50 years. Is that a fact or fiction, would you say?
So I think it's a fact out of context. And let me explain what was happening. So one of the surprises, one of the lessons that we learned from the paleoclimate record, climate, at least locally, doesn't always change slowly. There can be what are called abrupt changes. That being said, the best examples of abrupt changes are not really global, or at least they may have some larger than regional impacts, but they're not. But to say that the whole world warmed by 15 degrees is a gross misstatement. Where this comes from is the ice core records from Greenland. They're very interesting. Ice core records from Greenland are very different from Antarctica, partly because Greenland is really not a polar glacier. It's a more temperate glacier. It's high latitude, but it's not sitting up at the pole. And during the last ice age, between 20,000 years ago and say about 70 or 80,000 years ago, Greenland shows some very interesting and very large temperature changes where there was abrupt warming. And as you said, it's between 10 and 20 degrees Celsius of warming. And it happened in some cases extremely fast, not faster than 50 years, and probably in just a few years. So this is extraordinarily fast warming, 10 or 20 degrees Celsius in just a few years. And then temperatures would slowly cool down and then very abruptly cool down. Again, in just a few years, they would return to their very cold state they were in during the last ice age. So those are called Dansgaard-Oeschger events, named after two Scandinavian scientists, Hans Oeschger and Willy Dansgaard, who are pioneers in the ice core field and helped sort of discover these cycles. The mistake that people have made is that they've therefore assumed that the Greenland ice core implies that the whole northern hemisphere was changing by that much. And it turns out that's really the mistake. So what you're saying is exactly correct. Records from Greenland do show, and there was a big one that happened about 15,000 years ago during the deglaciation. But these very abrupt warmings happened, but they really appear to be very local in scope. That is, they had a huge temperature change on the top of the Greenland ice sheet, 3 kilometers above the surface. If you actually went to Europe, you would see them, but they would be much more subtle. They might be fractions of a degree, or maybe 1 or 2 degrees or something like that. You see similar patterns in caves in China that have to do with precipitation patterns and the changes in the jet stream. But again, much more subtle. They're not huge temperature changes. So this isn't a global change. We actually think it has to do with the distribution of sea ice and the very large amplifying effect of the ice sheets. And in fact, what's interesting is you don't see these kind of variability when the ice sheets melt and they go away. So since about, 10,000 years ago, we don't see any variability like that. In fact, the name for the recent period, the Holocene, is named because of its climate relative stability. So that's kind of interesting.
That's very good context. And we talk about 1.5 to 2.5 degrees Celsius, and I go, civilization will survive that. Might be unpleasant, but 15 degrees C in 10 years, we'd be completely fucked. Glad to hear that seems unlikely.
Yeah, that's not going to happen. But it's at the same time, don't underestimate how big a change 1.5 degrees is. 1.5 degrees Celsius is a lot of temperature change. Just to give some perspective on this, the difference in global temperature between the glacial maximum 20,000 years ago, when we had an ice sheet covering half of North America, the ice came, where I'm sitting in Boston was under 1 kilometer of ice. Down in New York is where the glaciers ended. You had all of Canada being covered by ice, part of the northern US. There was so much ice on continents 20,000 years ago that sea level was about 130 meters lower than today. That's how much water was taken out of the ocean and put onto land in the form of snow and ultimately ice. So that's a big deal. And the global temperature change was about 5 degrees Celsius. So think about when you talk about 1.5 or 2 degrees warming, you have to calibrate people. 5 degrees is the difference between the last glacial maximum 20,000 years ago and today. So 2 degrees is still a really big deal. And 5 degrees warmer, is like a completely different planet.
So if we go to 5, it's very, very, very bad. And I guess that's about where we get if we burned all the coal. It might even be worse than that.
Oh, absolutely. But I think it's important to understand, I've been giving talks recently to public audiences on climate change, and there's so many details and there's so much complexity in climate science. I've tried to distill down what I've learned over 25 years of thinking about this problem. And I think there are 2 essential elements that everybody needs to understand. And the rest is detail. The rest are fascinating details, and we could talk for hours about those details. But the 2 really important elements are, one, that this is fundamentally a collective action problem that is global. And humans are really bad at collective action problems. And when I say that, I mean that this isn't about just China or the US. And it really requires global cooperation to fix the problem. Doesn't mean that every last person needs to be completely fossil free, but essentially world society needs to stop using fossil fuels, and we need to stop increasing CO2 in the atmosphere. The second part of the problem is that every aspect of the problem has long timescales. And put together, those two components are killer. I'll talk more about what that means, these long timescales, but I mean the timescale of the climate system, the oceans, the ice sheets, also the timescale of the carbon cycle, which is unbelievably long. And finally, and this is the part that a lot of people in the technology world or who think about innovation don't really understand, which is the timescale for energy. The energy system is also unfortunately very long. This isn't something we can actually, change. We can't turn on a dime that quickly. But I think that's really fundamental because we're dealing with a global collective action problem, the likes of which we've never really dealt with before, and coupled with long timescales. And humans are really bad at both of those things.
Yep, thank you. We'll get into a lot of those topics as we go along, but I like to particularly call out collective action problems. One of the things I've highlighted again and again in the whole problem of how we build a social operating system. And the best book I've ever read on the collective action problem is by Mansur Olson. It's a book called The Logic of Collective Action. And I'd encourage our listeners to go read that book if they want to know more about how hard it is for groups of people to actually get together and do the right thing. Let's move on to a little bit more detail. In discussions of climate change, we hear a lot about climate models, ensembles of climate models. I've seen these graphs with the whole series of climate models laid over each other. How relevant are they? What do they tell us? What do they not tell us?
Well, climate models are very important tools for those of us studying the climate system, both in terms of trying to understand mechanisms and also thinking about forecasts for the future. But I think it's really important to understand that we're doing an experiment on the planet that hasn't been done ever in geologic history. There are some analogs. The best natural analog we might talk about is about 55 million years ago. But it's a decent analog, but it's not a perfect analog because it happened on a much longer time scale. So the truth is that we really don't know a lot of things about the Earth system and how it's going to respond to the kind of changes we've made to the atmosphere. And so models are really important because the system is too complicated to just, do a calculation on a blackboard or a piece of paper and predict exactly what's going to happen. At the same time, we have to always maintain a sense of skepticism and questions about the models because there are parts of the system we don't understand. That is, they represent the best understanding of the Earth system, but we're taking the Earth system outside of any realm of experience. And therefore, the history of observations is only limited in its ability to predict the future. Does that make sense?
Absolutely. And, we both tend to think in terms of complex systems. And we do know that the ability to predict complex systems out a ways under major perturbation is relatively limited. Best we can do is build various models and maybe some sense. We can't call our shots.
Yeah, although again, I think what's important for people to understand is that for the basic physics of this, it's not that complex a system. The basic physics of the greenhouse effect and the basic physics of how the system worked was known more than 100 years ago. John Tyndall understood the basic physics of the greenhouse effect. He did these elaborate experiments showing how carbon dioxide would absorb infrared radiation. And Svante Arrhenius basically, he, for those of you who don't know who he was the first Nobel Prize winner in chemistry from Sweden. He was the first Nobel Prize laureate from Sweden. He's considered one of the founders of physical chemistry. And in around 1903, 1905, he was already writing about the greenhouse effect. And he actually suggested that we would probably double carbon dioxide levels because of burning coal, and that he calculated the effect would be about 4 degrees Celsius. So the basic physics of the system was understood more than 100 years ago. This is not new science. It's not unbelievably complex. Yes, the Earth is a complex system, and most of what we don't know are things that could hurt us. But But the basic physics of how the Earth warms is actually pretty understandable with relatively simple models that are not that complex. And what I mean by that really is, the basic idea of the radiative equilibrium. So when you increase greenhouse gases in the atmosphere, we understand, again, going back to John Tyndall and Svante Arrhenius 100 years ago, we know that the Earth's going to warm up. And that's just because we've increased essentially the absorption of infrared coming off the surface. Essentially, we've increased the boundary layer. You could think of it as putting a thermal blanket on the Earth. And as a result, the surface temperature is going to heat up until the outgoing radiation balances the incoming solar radiation. That's very simple. What's more complicated, if the Earth were completely covered with land, climate change would be so much simpler, because essentially it would very quickly warm up and would achieve that radiative equilibrium, and we'd be all set. But the fact that 70% of the Earth's surface is covered with water makes the Earth much more interesting and complicated. And the reason is that the ocean is this huge heat sink. It's a giant tub of cold water. Think about what would happen, in your bedroom if you had a giant bathtub that covered 70% of your bedroom and was a big ice tub filled with ice water. And now you turn up the thermostat so you can sleep there to 70 degrees or 68 degrees or whatever. And what you discover is it's still really cold in your room for a very long time. And that's because the heat is going into warming the ice, and there's heat exchange, and the ice bath is cooling the room. And you have to wait for that ice bath to warm up before you reach an equilibrium temperature. The same thing's happening with the Earth. So the ocean is absorbing heat and mixing it down. And if you actually look at the pattern of warming, the spatial pattern of warming, you see that the continents have warmed about twice as much on average as the oceans. And that's because the oceans are actively sucking up heat. And that's both good news and bad news. The good news is we haven't really had to experience the full impact of our changes in the atmosphere that we've made. The bad news is that we're committed to probably at least 50% more, and maybe more than that, maybe 70% additional warming that we've already experienced is still to come into the future. So if we stopped burning fossil fuels tomorrow, the Earth is going to keep warming for centuries, maybe even millennia. That's a little scary.
Could you explain that? I know that it's true, and I've gone through the math myself, but it would be great if you could explain how that thermal inertia works in as plain a language as you could.
Well, I think it's exactly the same as the example I gave with the bathtub in your bedroom. Essentially, the oceans are a giant heat sink. So when you increase greenhouse gases in the atmosphere, the Earth wants to achieve a certain temperature that will achieve what's called radiative equilibrium. That's when outgoing infrared radiation, that is heat, that goes out to space, is equivalent to the amount of energy coming in from solar radiation. So when you add greenhouse gases, you create an imbalance. You absorb more of the infrared radiation, and therefore the surface temperature has to rise to achieve a new equilibrium so that you're in balance again. What comes in has to go out. 90% of the imbalance today actually goes into warming the oceans. A few percent goes into warming the surface. A few percent goes into warming to melting ice. But 90% of the energy imbalance, because of the greenhouse gases we've added to the atmosphere, goes into heating the ocean. So if you sort of say, what is global warming? The answer is global warming is really ocean warming. That's where most of the energy is actually going. And the time scale of mixing of the oceans, mixing all that cold water up and eventually warming the whole ocean, or at least the whole upper half of the ocean, the time scale is thousands of years. And so until the ocean is in equilibrium with this new atmosphere, essentially it's going to keep absorbing heat and keep warming. And that's going to take more than 1,000 years. So we've already committed the Earth to substantial additional warming that we haven't yet experienced. Does that make sense?
Absolutely. I'll play it back in as plain English as I can for our audience. The ocean is storing energy, and the result of that, as it mixes thoroughly, is that the average temperature of the upper layers of the ocean will gradually rise, and then that warmer water sitting next to the atmosphere will slowly raise the temperature of the atmosphere.
That's right. So for example, 20,000 years ago, when the Earth was about 4 or 5 degrees colder, The deep ocean was about 4 degrees colder as well. The deep ocean was very close to the freezing point of seawater, which is about -2 degrees. Because of salt, it's below 0 Celsius. So, the ocean was much colder 20,000 years ago. And you could think of the fact that the ocean was sort of more in equilibrium with a colder climate. By the way, carbon dioxide levels were about 180 parts per million back then. That was one of the reasons why the Earth was so cold. So in the last 10,000 years, carbon dioxide has been between 260 and 280 parts per million. And the atmosphere and ocean have equilibrated to the point where the ocean is, about 1 or 2 degrees in the deep ocean. In the Atlantic, it's a little warmer. It's about 3 or 4 degrees because it's a little saltier. But essentially, that is in equilibrium with the modern atmosphere, or with the pre-industrial atmosphere. Now that we have added greenhouse gases, the oceans are slowly warming, and probably they will warm, another 3 or 4 degrees. And we've just started. The heat uptake from the ocean is happening steadily and slowly. And in fact, it is one of the major reasons why sea level is rising. Certainly, ice melting is contributing to sea level rise, but one of the major reasons for sea level rise is just thermal expansion of seawater. That is ocean warming.
Very good. Very well stated. I think that will help our audience understand how important this ocean warming phenomena is, both with respect to its long-term inertial effects. And this is very important for people to know. Most of the sea level rise we've seen so far is just as Dan said, the water gets bigger when you heat it up. Another issue about the ocean, which we hear talked about a lot, is acidification of the ocean. What's your take on that?
So I actually think acidification, first of all, people have to understand the actual change in pH of the ocean is actually pretty subtle. First of all, the ocean is slightly basic. The pH of seawater is about 8.2 or 8.3. The deep ocean, it's a little bit less than that because of the biological pump that actually takes biological productivity, algae, bacteria, falls to the deep ocean. It gets respired by zooplankton. They eat it and turn it back into carbon dioxide, which slightly acidifies the deep ocean. So the deep ocean is a little lower pH than the surface ocean, but both are more basic than neutral, right? So they are both well above 7. Ocean acidification really has to do with the time scale of the carbon cycle. We're adding carbon dioxide to the atmosphere more quickly than the ocean can absorb it. And the reason is because the ocean only mixes so fast. If we could mix the oceans instantly, if we had a giant mixing rod that would mix the oceans very quickly, 80 to 90% of the carbon dioxide we've added to the atmosphere would go into the ocean. So in the long run, you could say that the solution, or at least 80 to 90% of the solution to pollution, is dilution. That is, the ocean's going to take care of our problem. The difficulty is the time scale for that ocean uptake is probably several thousand years. And so 80% of the CO2 is likely to go away, but only over the next several thousand years. And therefore, we have to still live in the next few centuries. And so we've got a problem. Because of that disequilibrium, because CO2 is going higher in the atmosphere and the ocean isn't taking it up fast enough, the surface ocean, which mixes and equilibrates with this atmosphere relatively quickly, that is the upper 100 or 200 meters of the ocean, is actually seeing higher levels of carbon dioxide, and its pH is dropping a little bit, like 1/10 or 2/10 of a pH unit. So it turns out that's actually a pretty subtle effect. What it tends to do is make it slightly more difficult for organisms that make their shells out of calcium carbonate. And we're talking about corals, we're talking about clams and other mollusks. We're talking about algae called coccolithophores. They grow their shells out of calcium carbonate that then fall on the ocean floor and form limestone or chalk. And this slight change in pH of seawater can affect the ecology of those organisms. Now, it sounds very scary, and some people say, oh, ocean acidification, it makes it sound like the whole ocean is going to turn into acid and everything's going to die. That is really not true. In fact, I would say that the total effects of ocean acidification on the ecology of the ocean right now are still mostly unknown. I don't even know in what direction they're going to go. Certainly, they're going to probably hurt coral reefs and favor organisms that don't grow their shells out of calcium carbonate. But I would say this. First of all, by far the biggest impact on the ecology of the oceans that we've experienced so far is overfishing. We have basically ruined the marine ecosystem just by taking so many fish out of the ocean. And so ocean acidification is sort of low on the list of major concerns relative to overfishing. The second point is that the warming itself, that is climate change itself and the warming of the surface ocean, is profoundly changing the ocean ecosystem. And that probably is going to have a much bigger effect on ocean ecology than the acidification. So it's not that ocean acidification is a non-issue. I just think it's really a minor issue relative to warming of seawater and also the impact of overfishing. We've just devastated. And overfishing includes, by the way, the trawling of the oceans. That most of the continental shelf, that is the shallower parts of the oceans, we've just dragged sleds over it and just completely destroyed it, like dragging a heavy rake over. Essentially, it looks like pavement now instead of a natural ecosystem. It's just horrible.
Well, thanks for putting all that into perspective. I think that's very useful. What about the data? How good is our data about the actual levels of climate increase? And how does the data that's been collected and cleaned compare to what we've seen in the models?
So I would say that in general, our observing system of the Earth is, I would say it's a half empty, half full kind of problem. The answer is there are some great successes, especially recently. There are also some places where we could do a lot better. There are certainly parts of our Earth observing system we'd love to have more carefully calibrated data. One of the challenges with certain types of climate data is that it can be spatially variable. So think of the problem of recording precipitation. We know this from Santa Fe. You can be in New Mexico and there can be rain in one place and no rain in, 3 miles away. It's highly spatially variable. So actually recording average precipitation rates is actually pretty complicated. And if you want to do it globally, including in places where they don't necessarily have the same infrastructure that we have in the US, it gets really complicated. So, for example, most of the studies of what the impact of climate change on agriculture is going to be is from the US because that's where the good data are, or maybe sometimes from the EU. We really don't have very good data from Africa or certain parts of Siberia or Latin America. And that's partly just because the quality of the observations is too low. The satellite era has helped in some respects, but in some cases, there really is no substitute for good ground-based observations. Another problem with climate change is that observing systems change over time. A classic example of this is measurements of ocean temperature. There are scientists who still argue over correcting, back in the day, there used to be buckets that people would use on ships. They would use cloth bags to take seawater and then measure the temperature. And merchant ships would actually do this. And then they used to switch from cloth buckets to metal buckets or wooden buckets. And then you actually switch today. Most ocean measurements are made on merchant ships using an engine intake system. And it turns out that every time you change the measurement system, there are actually some systematic and subtle changes in the temperature that you measure. And you have to correct for these errors. And the problem with climate change is you need absolute calibration with very high precision. And that's a very big problem. So when you change the measurement system, you kind of have to think about the calibration problem. And that's always been a problem for Earth observations. Let's talk about some of the good news, though. The good news is that, 20 years ago, most of our observations, say, of the ocean warming, which, as we said, is, that is global warming, is ocean warming. 90% of the energy is going into the warming the ocean. Most of that information, in fact, all of it really came from a bunch of cruises where oceanographers would go out and tow a wire, drop a wire over the side with a thermometer and basically measure the temperature with depth and then come up and, and they would do a transect at some point in the year. And then some other crews would go out and do another one. And that's how we knew about the ocean. So it was kind of awful. There was a great quote from Hank Stommel. Hank Stommel was a famous physical oceanographer. He was at Harvard and MIT and mostly at Woods Hole. Hank Stommel, he remarked that the determination of climatological conditions in the atmosphere by means analogous to those used by oceanographers would be to use half a dozen automobiles and kites to which air-sounding instruments were attached, and by doing all of their work on dark, moonless nights when they couldn't see what was happening in their medium. So for the history of oceanography, that's how oceanographers studied the oceans. They went out on ships and they dropped wires and measured what was down there. They couldn't see, and they would go out randomly on ships and measure. And so there are parts of the ocean that just weren't measured. And you certainly didn't have long time series. Starting in the 80s, we had a few places where we would actually install moorings and get continuous measurements, but they were just a handful of spots around the oceans. And only shallow, not very deep. So, we really didn't understand the oceans in terms of an observing system. All of that changed in the 2000s. We created a system, and it's really something that hasn't gotten enough attention. It's called ARGO, A-R-G-O. And these are floats. These are floats that actually sit down at about 1,000 meters in the ocean, and they sit there. They're not driven. They're just, they randomly drift, but 1,000 meters, the currents aren't very strong. So they sit there for 9 days. And then on the 10th day, they slowly drop down to about 2,000 meters. And then they slowly rise up to the surface and record the temperature and the salinity every 10 centimeters. And that takes about 6 hours. And when they get to the surface, they beam the data back down, back to a satellite, and then they sink back down to 1,000 meters and sit there again for 9 days. And these are automated floats that have a lifetime of about 5 or 6 years. And it's kind of incredible. There are currently something like 4,000 floats out there around the world oceans. And what's amazing is there's something like 30 nations that have all contributed to this program. This is an international partnership for Earth observations that has been extraordinarily successful. So in just a few years, we had collected more data on the temperature and salinity of the ocean than in the previous 100 years of oceanography. That's how it's a revolution in Earth observing systems.
That sounds really interesting.
It's amazing. And so we have data now over the last about 15 years and we can actually measure the ocean warming. So now it's not a speculation whether the ocean is warming. We measure ocean warming. And if you sort of say, do we know if global warming is happening? The answer is yes, because if we can measure ocean warming, that's where 90% of the energy is going. That absolutely proves what's actually going on in terms of the radiative imbalance. And I think that's really fundamentally important. So that's a great success of Earth observations. In terms of the models, the answer is the models are good, but not perfect. There's a lot of details of the real world that they don't have, some of which I think are important for sort of intermediate timescale forecasts. I'll give you an example. One of the things the climate models don't do very well is they don't actually simulate the kind of decade to decade variability that we see in the real system. And many of us think that the reason for that is that the resolution of the models just isn't good enough. They're not actually simulating the mixing, the eddies, the complexity of the turbulent flow in the oceans because their grid spacing is just too big. And so it smears it all out. And so the result of that is they don't have some of the physics in it that produce some of the decade to decade variability. And therefore that limits their skill in predicting the future, at least on intermediate timescales. That doesn't mean they're wrong altogether. It means that, if you say how well are climate forecasts of, what the temperature is going to be in 2040 or 2050, the answer is there's a fair amount of uncertainty because of the decade to decade variability that we see in the real system. And we know the models don't do that very well. That being said, if you go further out, they actually probably have more skill because the overall temperature rise is greater. And I think the most important thing to understand is the biggest uncertainty in all of this is actually what humans are going to do. We don't know how much greenhouse gas we're going to put into the atmosphere over the next 100 years. And so by far the biggest uncertainty in climate forecasts is actually the human part of the system.
We'll get to that later, but yeah, thanks for that. Now, the bottom line, does the last 15 years of this system, was it Argo, did you say it was?
Argo, yeah.
What does it show about the data in the last 15 years?
Well, it shows that the oceans are warming, and it's warming at about the rate that people are predicting. The error bars will continue to go down as we get longer time series. So right now we only have, about 15 years. We'd like to have more. But, in general, it's mostly consistent with the models, and the models are slowly converging. It used to be that there was a big argument among climate models. This goes back to the early 80s. The early days of climate models in the 70s and 80s. In the US, there were two main groups. One was at GISS, which is a NASA lab in New York, and the other was at GFDL, which is at Princeton, New Jersey, and a NOAA lab, National Ocean and Atmosphere Administration. And the NOAA work was pioneered by a scientist named Suki Manabe, a great climate scientist who pioneered development of climate models. And the work at GISS was led by a guy named Jim Hansen, who is one of the heroes in climate change. He gave a famous testimony to the Senate in 1988 that changed a lot of people's thinking about climate change. Anyway, Jim Hansen's model and Suki Manabe's model, they both did runs with doubling of carbon dioxide, and they got different answers. I think Suki Manabe's model got 2 degrees Celsius and Jim Hansen's model got 4 degrees Celsius. I think that's right. I could have gotten it backwards, but I'm pretty sure that's the right order. It doesn't really matter. One got 2 degrees, the other got 4 degrees. And so a famous scientist at MIT named Jules Charny said that the climate sensitivity, which we defined as how the Earth responds to a doubling of carbon dioxide levels, was about 3 plus or minus 1.5 degrees. In other words, he just split the two numbers and said, okay, the number is 3 because you got 2. One group got 2, the other got 4, so the right number is 3. Obviously, that sounds a little arbitrary. And there was a big discussion about, is it 1 or 2 degrees or is it 3 or 4 degrees? And the answer matters, right? If doubling of carbon dioxide level, which seems inevitable soon after mid-century for the Earth, we're guaranteed to get there. The question is how much higher we'll go in terms of carbon dioxide levels. But doubling of CO2, if that actually produces 3 to 4 degrees of warming instead of 1 to 2 degrees of warming, that's a really big deal. We need to understand that. And what was interesting was most of the climate models, when they were compared against recent data over the 20th century, suggested that the number was small, was probably closer to 2 degrees. And the interesting thing was those of us who studied the paleoclimate system, the last ice age, or the ancient climates of the Eocene 50 million years ago, we realized that in fact, if it was only 2 degrees per doubling of CO2, you actually couldn't explain the changes in climate we'd seen in the geologic past. We had a pretty good idea of how much carbon dioxide levels changed, and you couldn't explain that with just 2 degrees per doubling of CO2. You needed something more like 4 degrees. And so there was this argument about, was it 2 degrees or was it 4 degrees? Most of that has gone away, and here's the simple resolution, and again has to do with timescale. It's really interesting. The timescale of warming and the timescale of the oceans. The models, when they compare to 20th century data, they're looking at the short timescale. They're looking at the immediate response of the Earth system. And again, if a substantial fraction of the warming has not yet happened because of ocean warming and the timescale of ocean mixing, that actually reconciles the two perspectives. So the climate sensitivity of the models due to, a doubling of CO2 on the short time scale is probably closer to 2 degrees Celsius per doubling. But if you wait for the oceans to warm, then it gets closer to 3 or 4 degrees. And that's where now everything has sort of come into agreement. I know that's a bit of a long tangent, but I think that's important to understand.
Yeah, I think that's very important because, a lot of the conversation, talking about policy, focuses on like 2100, but it is important, and we actually have to do something before 2100, a lot. But it's also important to realize that we've pulled the slingshot way back, and it'll be impacting 2200, 2300, and 2400. Though hopefully we'll have techno fixes by that point, which we'll talk about here in a minute.
Well, I would caution you, Jim. First of all, the last thing you should ever do, and please don't ever do this again, is to call geoengineering a techno fix, because it's not. It is absolutely not a techno fix. I would purge that word from your vocabulary with regard to climate change, because there is no techno fix. The thing that people need to understand is the timescale of the Earth system is really long. And this gets into this question of human response. We see this all the time. And I know you don't want to talk about politics. I'm not going to talk about politics per se, but I will say that a lot of the rhetoric from environmental groups and from political candidates who want to do something about climate change, they struggle with this because they know that people who care about climate change want them to fix it right away. And the problem with climate change is it's a long time scale problem, and it can't be fixed overnight. You can't decarbonize the US in 10 years. And even if you could, it wouldn't solve the problem, because it's a global collective action problem. And you can't decarbonize the whole world in 10 years. And even if you did that, again, the timescale for the Earth to keep warming is still millennia. And so, you're not going to fix this problem quickly. It just is not possible. And I think that's really, really important to understand. Let me give you a perspective on this. We haven't talked about the ice sheets yet, but the ice sheets have a terrifying long time scale. I think people maybe understand a little bit intuitively how big the ice sheets are, but I want to give people an example of just how large they are. So Greenland is the smaller of the two polar ice sheets. Greenland is not really polar. It's more temperate. Antarctica is much bigger. So if Greenland melted completely, sea level on average would rise about 7.2 meters, right? Or about 23 feet. That's tiny compared to Antarctica, which is 50 or 60 meters of sea level equivalent. But what I think people don't understand is just how big that really is. So, Greenland is so big, it actually has its own tidal force. A lot of people have never heard this, but it's very interesting. So let's imagine you melted, suppose we waved a magic wand and we melted a seventh of Greenland. Okay. So you melt a seventh of Greenland, and on average, sea level rises by 1 meter. Okay. But that's a global average. It turns out that if you were standing in the southern tip of Greenland, you would see sea level fall about 19 meters.
That's interesting and strange.
Do you know why that is?
No, tell us. That sounds very interesting.
It's because of the gravitational pull of the mass of the Greenland ice sheet. That is, just like the moon pulling the water around, which is what causes the cycle of tides that we're used to. The Greenland ice sheet, it's so massive that it's actually pulling seawater towards it. So when you lose a seventh of Greenland, you lose so much mass that the sea level locally recedes because it's got reduced gravitational attraction. Even though on average sea level is rising 1 meter, it's falling by 19 meters right next to Greenland. Isn't that incredible?
That is wild. That's a new thing that's worth knowing.
But the interesting part of that is, if you think we can actually physically control something as big as the Greenland ice sheet, I think you should think again. This is a very big engineering challenge. And by the way, Greenland is tiny compared to Antarctica. And there's a big difference between the two ice sheets. The cause of mass loss from Greenland is mostly, and the risk for the future is mostly due to summer melting. So every summer, Greenland melts on the periphery. Sometimes in 2012, it melted just about everywhere on Greenland, but most years it only melts in the perimeter of the ice sheet. And then in the winter, more snow falls. And the net today is negative. That is, it's losing mass. It's contributing something like a little more than half a millimeter a year, close to probably somewhere between half and 1 millimeter a year, something like 0.8 millimeters per year, based on data we have from a satellite that measures the gravitational field of the Earth. So 0.8 millimeters per year, that's not that much, right? Think about that. That's 0.8 millimeters a year is like 8 centimeters over a century. That doesn't sound so terrifying. The problem is we've seen very dramatic changes in the last 10 or 20 years. And so the concern is that this could dramatically accelerate. And the risk is much more intense summer melting in Greenland. In Antarctica, it's melting more slowly. It's probably closer to a half a millimeter a year of mass loss. But what's interesting about Antarctica is the mechanism is different. Most of Antarctica, the peninsula is different. We heard a report recently in the news that it was like 67 degrees Fahrenheit in Antarctica for the first time ever. But that was in the peninsula. That was pretty far away from the core of Antarctica. Most of Antarctica is way below the freezing point. And therefore, even in the middle of the summer, the Antarctic summer, it's still well below freezing. And so it could warm quite a bit and still not melt. And so some scientists actually think Antarctica will gain mass sometime this century because the snowfall will increase and exceed the amount of ice that gets lost at the edges. But what's scary about Antarctica is something else. The mechanism for mass loss from Antarctica is not summer melting because it's so cold. It's actually the flow of ice into the ocean. And right now, that flow is being impeded by large pieces of ice that are floating on the ocean called ice shelves. The recent Pine Island ice shelf has been breaking up, and it was in the news recently. An enormous iceberg the size of Rhode Island dropped off or something like that. But the big concern is that if we lose the big ice shelves, and the biggest ones are called the Ross Ice Shelf, the Ronne Ice Shelf, those ice shelves act a little bit like corks in a bottle. They actually keep the glaciers sitting near the coast from flowing into the ocean. Now, the ice shelves themselves don't change sea level because they're already floating on the ocean. They're already displacing seawater. But if they break off, suddenly there could be very rapid flow of ice from the land into the ocean, and that would affect sea level. And the scary thing about that is not the timescale. They're not. It's not going to happen overnight because fundamentally, glacial flow can only happen so fast. The scary part is that glacial flow doesn't care what the surface temperature is. It's really driven by gravity. These glaciers are flowing downhill, and once you lose the barrier, you lose the ice shelf, there's really not much we can do about it. You've now committed the Earth to probably centuries to maybe millennia of continued sea level rise, maybe 10 or 20 meters of sea level rise for the next millennia. And future generations are just going to have to deal with it. And so we've made decisions now that affect the Earth for thousands of years, and we're not thinking about it that way.
That's an interesting thought. Glad I live at 2,200 feet. Not going to be pretty for a whole lot of the world's population that lives within 10 meters of sea level. And that's what, 1 billion people, something like that?
Yeah, although I got to tell you, if the time scale, this is again one of the fascinating parts of climate change. Economists will tell you, look, over 100 years, you can move cities. Part of the problem of climate change, I've been watching what's happening with coronavirus right now around the world. People stopping travel, quarantining people, and thinking about how people are reacting to coronavirus versus reacting to climate change. Think about how different that is. I think it's fascinating to see how people deal with an acute situation and they panic. Nobody is asking, well, what's the cost benefit of cutting off flights to China? Right? We're just doing it. It's a public health issue. It's an emergency. We're canceling flights. We're shutting down Chinese cities. Literally, people are not allowed out of their homes in China. And by the way, that may be the right decision. I'm not questioning that decision. I'm just saying it's interesting how people respond to an acute concern, whereas the long time scales change everything. And here's what makes me uncomfortable. We're really not good at thinking about the economics or the ethics of long time scales. You can convince yourself that on a several 100-year time scale, economically, it makes sense to do nothing, let sea level rise and move people and adapt to it, because over a few hundred years, think about it. None of the cities we have in the world are more than a few hundred years old. I mean, obviously Paris, London are much older than that, but most of their buildings are much younger than that. You could rebuild them, no problem. And yet I have the sense that 200 years from now, people are going to, our descendants are going to look back at us with horror. They're going to say, what were they thinking?
Yep.
Look what they did to us. And yet at any step in the way, it seems logical and practical to do very little. And I think that's what's very troubling about this long time scale thing. We really don't know how to deal with long time scales and think about the long-term commitments. In economics, you deal with discount rates, and there's a whole discussion of what the right discount rate should be. But, I think they've confused something. Discount rates really ask the question, how much rationally should you pay to avoid some damage in the future? And they quite reasonably recognize that $1 today is worth more than $1 50 years from now, and therefore you should pay less to avoid something that's going to happen 50 years from now than to avoid something that's going to happen tomorrow. And that's fine. I think what's left is the moral, ethical dimension of this, which is we're talking about decisions we're making for literally thousands of generations of humans that haven't even been born yet. And so the question is not how much should we pay or how much are we willing to pay. The question is, what moral obligation do we have to provide future generations on this planet the same kind of opportunities that we have? And that's a very different question.
Yep, very well said. And it's actually worse than that, Dan. If we took the economic discount rates, we would still be taking more action than, let's say, the United States is taking today, because we know from cognitive science and behavioral economics that your typical non-scientifically educated person tends to discount things hyperbolically, even more extremely than the exponential that you get from fixed interest rates. And so our politics is driven probably to a significant degree by hyperbolic discounting, where the future disappears entirely, which is even worse.
Hyperbolic discounting depends on what the rate is, actually may be a better thing for the long term, because what hyperbolic discounting does is actually say the long-term future is not worth zero. Exponential discounting, the long-term future is literally zero. Asymptotes to zero. But with hyperbolic discounting, the distant future is worth something. It's just worth very little, and it's the same. So we don't distinguish between, and that's behaviorally consistent with experiments. When you ask people how much is it worth to you to avoid something 200 years from now or 500 years from now, the answer is it's worth something. It's just very, very little, and it doesn't really matter whether it's 200 or 500 or 1,000. So that's where the hyperbolic idea comes from. And so that is a little better in some ways than exponential discounting. But I think the whole discussion is still misplaced, because that's not really what the question is. It's not how much should we be willing to pay. It's a question of what moral obligation do we have. And that's a very different way of framing the issue.
Yeah, Murray Gell-Mann, I think you know Murray for sure, and I do too.
Absolutely.
Let he rest in peace, one of the great souls I've ever met. His strong proponent was that for calculating long-term impact on humanity, like climate change, that the only moral answer was to use a zero discount rate.
It's interesting. I think just the problem of the whole exponential discounting framework might lead you to that framework. My friend Partha Dasgupta, who's an economist at Cambridge University in England, Partha argues that for all we know, the appropriate discount rate is actually negative. That is, think about it. If the impacts of climate change are really catastrophic and actually erode the economy and result in negative economic growth, then the rational thing is to use a negative discount rate, which is, again, that's very controversial among economists, but I think it's an interesting question.
Yeah, very good. The other side of your work is analyzing, studying energy technologies and policy, including carbon capture and storage, low carbon synthetic fuels, et cetera. Why don't we start with an overview from your perspective on where we are with our energy technologies and which ones look like they ought to be ready within the necessary planning horizons to start to get us to a net zero carbon society in some reasonable period of time. I'm particularly interested, I mentioned all of them, particularly interested in carbon capture and storage. So let's give the Dan Schrag view on where we are with energy-related technologies.
So I think the answer is that because of interest around the world, including the US, but not necessarily focused here, there's a lot of good news. But the fundamental fact about the timescale of decarbonizing our global economy still holds. Let's review some of the good news really quickly. So if you think about 10 or 11 years ago when Obama first came into office in 2009, and he actually had a giant stimulus package because of the global because of our financial crisis, but it was really a global financial crisis. So he had close to $100 billion he was willing to spend on energy. And what's interesting to remember is that even 10 or 11 years ago, solar and wind weren't really high on the priority list. We talked about transmission, we talked about carbon capture and storage, we talked about nuclear, we talked about a number of things. And the reason was that solar and wind were still quite expensive. And in the last 10 years, that has been completely changed. Today, solar and wind, again, without storage, low penetration, but solar and wind are in most places in the US, that is reasonably windy places or reasonably sunny places, are actually much cheaper than any other form of generation, including very, very cheap natural gas, which is another big change in the last decade, for the US at least. So that is incredibly good news. We didn't think that solar and wind was a viable financial option 10 years ago. Today, it is. In Massachusetts, for example, 10 years ago, we were fighting over a project called Cape Wind, which was a big offshore wind project in Massachusetts. Here in Massachusetts, it's not very sunny and it's not very windy on shore, but offshore we have good wind resource. And so the idea was to build windmills, and they were controversial because the Kennedys didn't want it to obstruct their view off of Hyannisport. So there was lots of local politics and NIMBYism, that is not in my backyard. But in the end, one of the big problems with Cape Wind was that it was about 20 cents a kilowatt hour for the grid to buy. That's wholesale price. That's not selling to us. We pay residentially about 21 cents a kilowatt hour in Massachusetts. It's among the highest price of electricity in the country, maybe a little bit less than Hawaii, but as high as anywhere else. But the actual wholesale price of electricity is more like 6 or 7 cents. So 20 cents a kilowatt hour was incredibly high. Today, offshore wind is less than 6 cents a kilowatt hour in the UK. And there's actually projects being planned now for Massachusetts that are around 6 cents a kilowatt hour. That's incredibly exciting. In just 10 years, nobody would have predicted that kind of incredible cost drawdown for wind and solar. And so in some ways, the changes in prices mean that, at least for the next couple of decades, the whole world is just going to be building out wind and solar because it's so cheap. And that's really good news. But understand also that that's just the first step. Decarbonizing our economy involves lots of different steps. I think another bit of good news is that electric cars have emerged as what looks to be a viable alternative to gasoline-powered vehicles. And I think maybe not in 10 years, but in 20 years, I suspect that we will see, 20 to 50% of new vehicles sold in the US being electric. At least I hope that we'll get there. Right now, the price still needs to come down a little bit, but I suspect that will happen the same way it did for solar and wind. Currently, electric vehicles are about twice as expensive as a gasoline-powered equivalent vehicle. And there are range concerns because we don't have enough charging stations. But I suspect over the next decade or two, many places will solve that problem and the prices will come down. Many car companies are investing in that. Last year, or in 2018, 2% of new vehicle sales were electric vehicles. And I think that number will slowly grow. And that's a good thing too. And that's going to happen all over the world. The bad news is that probably only gets you 30 to 50% of the way to where you need to go. And first of all, that has to be global. So you have to get all the countries in the world to do it. And then there's the really hard stuff. How do you get rid of diesel fuel for trucks or trains or ships? How do you get rid of heavy industry, cement plants, the emissions from that, smelting? How do you get rid of jet fuel? Those are really hard problems, and there are a variety of ideas, but they all look very, very expensive. And frankly, those are going to be the hard parts of decarbonization. And I don't think we're likely to get started on those in a very serious way. I think we'll see early experiments and, little startups and things, but I don't think we'll have serious market for those things for several decades into the future. Policy is going to have a big role. We need to, enact policies that will accelerate this timescale. But from my perspective, I think we're fooling ourselves about how long this transition is going to take. I think if we're really committed and we had incredible political will, globally, it's going to take more than 50 years, and it could be closer to 100. I wish that weren't true. I wish we could accelerate it faster, but the numbers are really big and really difficult. And we also sometimes forget that it's global. In the US, we talk about, environmental movement talks about decarbonizing the US as quickly as possible. Everybody's focused on when are we going to get to zero emissions? And from my perspective, people sometimes forget that getting the US to zero emissions is actually not the goal. The goal is getting the world to zero emissions. The climate system really doesn't care about the emissions of the US. Now, that is not to say US shouldn't play or must. I think the US must play a leading role. I think we have an obligation as the world's largest economy and as the world's largest carbon emitter per capita to lead the world towards a solution. But understand that leadership means getting other people to follow. It doesn't just mean charging ahead. And so our goal should not be to decarbonize the US as quickly as possible. We have a much more difficult goal, which is to decarbonize the US as quickly as possible in a manner that makes all of the other countries of the world want to follow us. And that, unfortunately, is much, much more challenging because it can't just be that we do it. We have to do it in a way that looks attractive to others.
Indeed, indeed. Now, with respect to those concentrated energy sources that you mentioned, jet fuel, long-haul diesel, et cetera, doesn't biodiesels provide a potential entry point there? And also using carbon dioxide itself at some cost to produce liquid diesel precursors.
Absolutely. So I teach a course where I make undergraduates design a low-carbon economy for the U.S. And it's really difficult when they actually start to look at the numbers because, unfortunately, what you see is if you want to use biofuel and biomass can be turned into diesel fuel or jet fuel, there's a fabulous technology that was used by the Germans in World War II. It was used by this apartheid regime in South Africa in the 80s called Fischer-Tropsch, invented by wonderful German chemical engineers in the early 1900s. And you could take biomass and turn it into very high quality jet fuel or diesel fuel. It's fabulous fuel. And if you sequester the CO2, it could actually be carbon negative. And as you say, with a little bit more cost, you could scrub CO2 out of the air and add hydrogen and convert it to diesel fuel or jet fuel using similar technology. The problem, though, is cost. That's one problem. It's a lot more expensive. So, today, the global price of oil is around $70. But occasionally it falls to 40 or 50. Building a giant fuel plant to turn biomass into, say, biodiesel. By the way, the largest biomass refinery in the world that makes ethanol produces about 12,000 barrels of fuel a day. A small Texas oil refinery is about 100,000 barrels a day. So the scale is just wildly out of sync. So part of the problem is cost. So making biodiesel is much more expensive. And scrubbing CO2 out of the air and turning that into diesel is probably a factor of, 5 to 10 more times more expensive than petroleum. And so right now people aren't willing to pay that difference. But the other problem is the scale. If you start trying to get all of your fuel from biofuel, the amount of land area required becomes ridiculous. you end up with multiples of the US in terms of required footprint. So it isn't going to work. It's going to be interesting. I think for diesel trucks, things like potentially hydrogen fuel cell vehicles is an interesting idea. There's a company called Nikola Motors that's making trucks. I don't think it's likely to be on your interstate anytime soon. But I suspect in certain places where they could put in the infrastructure, there's a chicken egg problem. You need to have hydrogen fueling stations before anybody's going to invest in a hydrogen powered truck, because they can't drive a truck if they can't refill it. On the other hand, you can't really pay for making a hydrogen fueling station if there's no trucks that want to use it. So there's a chicken egg problem there. I think there's an interesting opportunity in a place like California, in the I-5 corridor between Sacramento and Los Angeles. I could imagine putting in, 3 or 4 hydrogen fueling stations and requiring that a certain fraction of trucks use hydrogen to clean up the pollution in the San Joaquin Valley. I think you might see regional experiments like that. But for now, that's going to be very limited. But I think in the long run, hydrogen is going to give diesel fuel and diesel trucks a run for their money. But that's going to take, I think, many decades before that happens.
And the other alternative, though it's decades long in building infrastructure, would be electrically powered trains to replace a fair amount of the long haul trucking, at least. It won't get rid of the short haul, but it'll at least get rid of some of the long haul.
So, in the US, you could imagine that. The challenge is that a lot of the long haul transport, we used to do it by trains. But the problem is we've torn up most of those train tracks. We've built suburbs and we've built bicycle paths, right? Think of all the rail trails that exist in every community that you know of. And most of the communities don't want to bring back railroads. And it's actually a very interesting part of the climate change dilemma that I think people don't understand. Decarbonizing our economies, whether in the US or anywhere else in the world, is really the biggest construction project that humans have ever attempted, by far. It is a massive capital investment. It's a massive infrastructure investment. And if you want to do it quickly, you can't allow the normal permitting process to happen. The truth is that today it's really difficult to build anything. A transmission line, a pipeline, a train track. Nobody wants it near them. Nobody wants the train tracks going next to their house. Nobody wants the transmission line impinging on their hike or their view or whatever. And so as a result, NIMBY, which is not in my backyard, has become banana, which is build absolutely nothing anywhere near anything. And that's a reality in the US. So what people don't understand is if you're really committed to climate change, you have to suspend kind of community permitting processes and just have total control and say, okay, we're going to build this pipeline there. We're going to build that transmission line there. We're going to put this train track in here. And people aren't going to like it. So, it works in China. It does in an authoritarian government. It doesn't work so well in the US. We don't build infrastructure quickly for good reason. People don't like being forced to suddenly have train tracks pop up near their house. Think about New York and Boston, for example, or New York to DC. Using 1970s French technology, we should have a train from Boston to New York that takes about 45 minutes. That's the TGV. That's not the fancy bullet train, Chinese or Japanese stuff. This is 40 or 50-year-old technology coming from France, the TGV. Why don't we have a fast train from New York to Boston? The current train takes a little under 4 hours instead of 45 minutes. It would be great economically for everybody. The reason we don't is because of Connecticut. The only person who can confiscate homes and build train tracks straight through from Boston to New York is the governor of Connecticut. And why would the governor of Connecticut ever seize people's homes of voters in Connecticut just so that people can go from Boston to Boston to New York quicker? I don't think that's ever going to happen. So I'm kind of skeptical that we're going to see in our system of governance that we're ever going to see the kind of infrastructure that we need to really fix this problem. So I'm skeptical on trains just because I don't think we're going to let them be built.
This is a little kind of Ruddian humor when the last general chairman of the Communist Party in China stepped down, Hu Jintao. I floated the proposal that the U.S. hire him, pay him $1 billion a year, and give him absolute authority to build as much infrastructure as he could get built in the next 10 years.
Yeah, there's one part of the U.S. that actually is really good at building infrastructure. They build things quickly, and they do it because they have a totally different attitude about it.
Texas.
And that's Texas, yeah.
Yep.
Texas is really good at it because they just do it. They don't have nearly the same restrictions on permit and process and community permission. They just kind of do it. And that's great. But it's also, I'm sure there are people who are upset about it in Texas too. So it's complicated.
It'd be interesting to see. I mean, as the millennials come online, who are clearly more concerned about climate change than us old farts, or in my case, old farts, your case halfway there, we'll be interested to see, are they willing to make trade-offs about things like having more trains or having biodiesel plants nearby, et cetera. We will see. If they're really, truly sincere about attacking climate change, they may well yield on some of these things. So I'm not as pessimistic as you are. Come back, 30 years from now, it may be that we see a resurgence of electric trains, both light and heavy. But that's a little bit unknown. And as you say, it is part of this collective action problem, which is at kind of the core of making this even more difficult than it is from a technology perspective.
That's right. I mean, again, if it were just about the U.S., decarbonizing the U.S., I think, people might be willing to kind of make the sacrifices. An inspiring example that some people use is World War II, where we had great sacrifice and we achieved and built far more for World War II in terms of tanks and airplanes and artillery units and everything else, far more than we expected in a very short amount of time. But people made real sacrifices. We spent 30% of our GDP on the war, more than 30% of our GDP for 3.5 years. It was an extraordinary sacrifice. I think if we could fix the problem that way, people might be willing to do that. But here's the challenge. It's a global. And so the argument, well, why would we do that and risk the rest of the world not following? If we don't know that China and India and Thailand and Myanmar and Pakistan and, Indonesia are going to actually do the same thing, why should we make these great sacrifices? And I think that's the collective action part. The free rider aspect is really tough to solve.
So there's one way to start to address it. It's funny you mentioned World War II. I'm working on an essay where I'm trying to calculate what the 1944 global GDP equivalent is to fix climate change. 1944 was the peak year of level of effort in World War II. U.S. was about 50% of GDP. Germany and Russia were at 70% of GDP. Japan might have been at 80% of GDP. And if you do that on a global basis, the number might be 30% of global GDP went into fighting World War II. So how many 30% of global GDP does it take to fix climate? And I'm working those numbers, and when I'm done with it, I'll publish the result. There is one way to get some traction on this collective action problem internationally, which is, suppose the U.S., the advanced economies of the eastern rim of Asia and Western Europe all declared that they were going to attack this at a World War II level of intensity, and that they were going to put in place tariffs equal to that cost from countries that weren't making that effort. So if China and India said they're not doing anything about climate, then everything that they export to all these advanced countries will get a very stiff tariff on them, equal to the imputed capital cost of removing that much carbon.
Interesting.
Yeah, that starts the cycle going. And particularly China and India are very dependent on exports to the advanced world. So here's a way, without having their agreement, we'll just put up walls and say, hey, the walls are coming. They start relatively low, but they grow very fast, very quickly. Maybe we start at a $50 a ton carbon equivalent charge.
So this idea of actually what's called, border adjustments has actually been around for a long time. Economists have been talking about kind of border adjustments and tariffs on carbon for 30 years, really, since early days of carbon pricing, because they wanted to make sure that it had an international component. Essentially forcing, at the time they were worrying about China, but now they'd be forcing other countries. The problem is that's good for a small number of rogue countries who refuse to play ball with the rest of the world. For example, if the US and China and the EU decided they would do this, they could possibly stick it to Russia or to India. But if, say, China isn't willing to play ball, frankly, I think India's dependence on the US or the EU is less than we think it is right now. And they could be quite sufficient, avoiding trade with the EU and the US, and mostly trade with China and Russia, for example, and do just fine. So I think trade and pressure on countries for climate change is a really important mechanism, and has certainly been part of the policy discussions for a very long time. But we understand that before you get there, you need to have most of the countries on board. Otherwise, it just doesn't work.
Yeah, I have to think about that and play a little game theory there, because one of the interesting things is that suppose China didn't want to go along. India then has an interesting opportunity to grab business from China, and I would say would apply for Myanmar and Vietnam. But anyway, let's move along here. Let's spend the rest of our time on geoengineering. You spend a lot of time thinking about it. There are opportunities here. There are risks. Tell us about geoengineering, starting with what it is, and then going through the risk rewards, models, preparation. What should we be doing about geoengineering?
Sure. So I think the issue of geoengineering, first of all, the idea has been around a long time. There was a report from the Johnson administration in the late 60s on solar geoengineering as a possible way of dealing with climate change. So again, this isn't a new idea. It's a very old idea. Edward Teller, the physicist, actually, I think was very attracted to this idea. I think that should make everybody a little reticent, knowing Edward Teller.
He was the father of the hydrogen bomb, by the way, right? One of the.
Well, yeah, although people would say Ulam might have been actually the father of the hydrogen bomb. But yes, he was certainly one of the father. He was certainly the champion of the hydrogen bomb, if not the father of it, maybe the godfather of the hydrogen bomb, and a very powerful influence on many presidents. Let's explain what it is. Solar geoengineering really is modifying the albedo of the Earth's atmosphere so that we could reflect more sunlight to space. Essentially, so as greenhouse gases build up in the Earth's atmosphere, we would add more reflective particles to the atmosphere, to the stratosphere, and or I guess you could do it low level as well. And so that we would reflect more sunlight back to space, essentially putting a sunshade on the Earth and cooling the planet to compensate for climate change. Now, the first thing to be said is that the physics of this are not totally straightforward. That is, at first glance, reflecting sunlight doesn't cancel out greenhouse gases. You should understand that the physics of this is different. That is, greenhouse gases in the atmosphere work 24 hours a day, whereas reflecting sunlight only works during the day when there's actually sunlight coming in. So right away, you have a change in the diurnal cycle that's kind of important. I think most people understand this from, if you go to the desert at night, for example, as soon as it gets dark, it gets quite cold in the desert because of clear sky, and the desert radiates heat back to space. Whereas if it's cloudy in the desert, it actually stays warm at night. And that's because the clouds add a lot of radiative absorption of infrared radiation, and it stays a lot warmer at night. It happens in the wintertime here in Boston too. The very cold nights happen when it's very clear. Whereas when it's more stormy, you don't actually get that cold. So at first glance, it doesn't fix the problem. It actually, reflecting sunlight doesn't cancel out more absorption of infrared radiation from greenhouse gases. What's interesting is when you put it in a climate model, it works a lot better than you expect. It actually works pretty well. It's not perfect. It doesn't perfectly cancel out the increase in greenhouse gases. And there's some interesting, what I call asymmetric effects. For example, plants, if you increased carbon dioxide level and put reflective particles in the stratosphere to reflect sunlight, to make it the temperature uniform, you could do that. But it turns out plants respond in interesting ways. Trees and plants actually, in response to the higher levels of carbon dioxide, they actually close their stomata, the holes in their leaves. And so they actually evaporate less water. And so they actually change the water cycle substantially in response to the higher CO2, because they are affected by the higher carbon dioxide levels as well. And so there's some interesting effects that you have to be very careful about. So it's true that in general, every place is probably better off if you were to magically solar geoengineer the planet, as opposed to just letting carbon dioxide levels rise. But that doesn't mean there aren't some big changes in some places. That's number one. The second thing that's really important to understand, though, and I think this is a good way of thinking about it. This is why, Jim, I don't like calling it a techno fix, because it's not a fix. I think a good analogy for it is actually something more like narcotics, morphine, for example. Narcotics can be a very important pain management medication. If you're having major surgery, say you're having major abdominal surgery for some condition, Jim, you would want some painkillers during the surgery, right? Anesthesia, you'll take that morphine any day, because having the surgery without any anesthesia would be excruciating. But if you only take the anesthesia, if you only take the morphine and never actually have the surgery, that's probably not a very good strategy either. Like morphine, solar geoengineering can be very addicting. That is, once you start it, you're kind of obliged to keep it going, because if you stop it on a very short time scale, the Earth would abruptly warm up, because now you're really far from equilibrium. And that would be terrifying. So let's just be clear on what we're talking about. We're talking about not a techno fix. We're talking about potentially a techno tourniquet that is going to take away potentially some of the pain, not all of it, but some of the pain. But it creates a variety of new problems and fundamentally doesn't solve the problem. Now, there are many people who are opposed to even thinking about this issue, the topic of solar geoengineering, because they say that it's going to delay action. If people think there's a techno fix, then they won't feel the pressure to reduce CO2 emissions. I personally feel that's really short-sighted. I actually think it's really important to think about this deeply, because, again, I think the timescale of climate change is so long that I think it's going to be very tempting for some either consortium of countries or individual countries to consider deploying a system of solar geoengineering sometime this century. I don't know who's going to do it. I don't know how it's going to get done. But I feel like as a scientist, as a climate scientist, I have a responsibility to think very carefully through how it might be done, especially to think about all the bad ways of doing it. And already I think we've learned something. For example, in the 60s through even just a few years ago, we were talking about sulfur, because that's how volcanoes can cool the climate. When a big volcanic eruption happens, sulfur dioxide gets emitted into the stratosphere, and it turns into sulfate aerosols that reflect sunlight and can cool the climate a little bit. And we've known this for a long time. So you could think of this as almost artificial volcanoes. People could scatter sulfur into the stratosphere and it would turn into sulfate aerosols and cool the climate. The problem is that it might also we think sulfur in this way might also affect the ozone layer. And if you sustained injections of sulfur for a long time, not just once from a volcano, but if you actually did this perennially for a very long period of time, you would potentially erode the ozone layer that protects us from UV radiation. That would be a very bad thing. And so we've learned that really from research on solar geoengineering. I think that's a really important example of why it's so important to think about this. It's not just how to do it, it's also how not to do it. Because, some political leader somewhere, sometime in the next 100 years, I think is going to find this very tempting, because it is relatively inexpensive relative to changing the energy system of the world. Now, to say that it's not a fix, I think that's really important. But I also think about this the way Churchill described democracy. Remember, he said something like, democracy is the worst form of government ever invented, except for the alternative. And I think of the same with solar geoengineering. Solar geoengineering is a terrible, arrogant way of fixing a more fundamental problem in the Earth system and in the human system. It's probably a crazy, terrible idea. Engineering the climate for every person, every living thing on the planet is terrifying. And yet it may be better than the alternative. And I think that's important for people to understand. Does that make sense?
Oh, absolutely. What are some of the risks involved? 'Cause if it was just a magic thing, we put, I remember some of the earlier suggestions. Oh, yeah, we add a little sulfur to the diesel fuel, let the jets just do their thing. But as you point out, that's not a good idea. But let's say some of these other ones that we don't have any known stupid risks about. What are the systemic risks, the complex system risks?
First of all, doing this in a model is very different than operationalizing this for the real world. Figuring out how to inject particles into the stratosphere in a systematic way that safely engineers the climate for every part of the world, because this particles mix, we don't control them, right? It's a global, you're affecting everything. You can't isolate it. You can't just do this for the US, or you can't just do this for China. It's much more complicated than that. Technically, that's a challenge, really doing this in a consistent way. Number two, the governance problems are enormous, maybe insurmountable. Think about who gets to control it. Often when we talk about this in the US, we just presume as the current global superpower that we're in charge. But do you really think that all the countries of the world are comfortable with somebody like our current president in charge of the thermostat for the whole globe? And who gets to decide? And by the way, whatever country or group of countries is in charge of this system, first of all, if anything goes wrong, they're going to get blamed. And here's the other thing. If there's a weather-related disaster, whether it was actually caused by the geoengineering system or not, they're going to get blamed. Right?
That's true. Just like hurricanes are being blamed on global warming, and global warming has some small part about it. Most of the hurricanes are driven by shorter term cycles of ocean circulation, but people can't separate those things.
So you're going to get blamed. If you actually do engineer the climate, you're going to have an awesome responsibility, and people are going to blame you for everything. So that's kind of daunting. And think about how we would feel if China decided to do this unilaterally. Would we really be comfortable with China having control over our climate? What if there was a big drought in the US like happened in 2012? Major drought, 50% of US counties in emergency drought conditions. Would we really be comfortable having China with their controlling the knobs? I think the answer is no.
And of course, that's part of the problem is that, we're tweaking a complex system with circulations within circulations within circulation. So even if we do a perfect job of...
There will be surprises. There will be surprises for sure.
Yeah. And local effects.
Absolutely.
It may work great for Argentina, but be a disaster for the Midwest of the United States or vice versa. And
we already know that to some extent. For example, research has shown that if you globally geoengineer the climate, things like, for example, in Indonesia, the Western warm pool of the Pacific, Indonesia is going to get drier. And so suppose there were rigorously verifiable impacts on particular regions or countries. So you knew that Indonesia was going to get drier as you did this. Would the US have to pay compensation to Indonesia? How would that work? I mean, here's what's interesting about climate change. I've been thinking about this in the context of how humans are likely to respond to the nature of the climate challenge and the energy challenge. And I've got to say, I think the one part that scientists often underestimate about humans is their ability to adapt to local challenges. We're incredibly ingeniously innovative and scrappy when it comes to fixing problems that affect us, that affect our communities. When it comes to long time scales, we're terrible. And there's good evolutionary reasons for that. And the same thing with collective action. We're really bad at global stuff. We're tribal. We see it in primates. We see it in chimpanzees. We tend to be tribal. We don't tend to cooperate very well globally. But here's the interesting thing. Climate change is a challenge the likes of which we've never experienced before. And I have a feeling that all of this is going to result in a lot of interesting innovation, not necessarily in energy systems, although I hope that happens also. But I'm thinking about how, if everything I know about climate change is right, it means that we're going to experience a lot of climate change, not just in my lifetime, whatever's left of it, but my children and my grandchildren and beyond. And that means that the reality of their impacts of climate change are going to drive incredible innovation in, say, in architecture, in agriculture, and possibly even in government. I actually think in the same way that, World War I led to the idea of the League of Nations that never really caught hold. World War II then resulted in the UN. I actually think climate change is going to require a new set of global governments, a new form of global governance that we haven't even imagined yet. I don't exactly know what it's going to be. But when I think about the issues like solar geoengineering, I don't think the UN is up for the task. And I don't think the framework of the Paris Agreement or anything else like that is really capable. I think something new is going to emerge. And it's not going to emerge because of altruism or because we all have some enlightenment. I think it's going to be because of necessity. H.G. Wells had a great line, I think it was in The Time Machine, where he wrote, "We are kept keen on a grindstone of pain and necessity." And I think there's a truth to that a lot of the innovation in the 21st century is going to come not because we're enlightened or we reach some kind of spiritual connection with the Earth system, but because, frankly, we're up against it. And we have to innovate or fail to survive.
All right. Well, I think this has been a very interesting episode, Dan. I think your closing remarks are a mixture of optimistic and but that's reality. I think our audience will find all this very, very interesting. Any final comments?
No, I hope you found it useful. It's a great topic. It's always good to talk about it. So I hope it's useful.
Production services and audio editing by Jared Janes Consulting. Music by Tom Muller at modernspacemusic.com.